Here we see a table of pendulum length in centimeters versus period in seconds. We're not going to worry about the physics of it, this being a mathematics class. In physics you'd certainly want to note that the length is measured in centimeters and the period in seconds, and it's not a bad idea in mathematics class, but just to focus on the numbers here, to focus on this as numerical data. I chose not to label that. As I think about it now, I wish I had, but I didn't. Now, from the physics, and of course we're not going to work out the physics of this situation, but from the physics we can say that if y is a power of x, if y equals x to the p, from physics we know that the period is going to be some power function of the length. We expect, or at least physics tells us that the period ought to be some specific power function, and what we want to know is what the power is. Now, just if y equals x to the p, we can see that if we take the log of both sides of the equation, we get log y equals log of x to the p, which tells us that log y equals p log x. Now what's this tell us? This tells us that log y is just proportional to log x. It's a multiple of log x. And in this case, if we graph log y versus log x, we're going to get a graph that has slope p. Again, assuming that y is a specific power function of x. So we'll have a slope p on the y on the graph of log y versus log x, which tells us that log y is p log x. That is, if log y equals p log x, the graph will have slope p. And the graph will also go through the origin. Now there are other power functions. We could have y equals some number like a times x to the p. And if we have y equals a times x to the p, then we're going to have down here a log of a times x to the p, which is log a plus log x to the p. So we're going to have p log x plus log a. And what that's going to do is change the y-intercept of the graph from the origin up to log of a, whatever that happens to be. But it'll still have slope p. So we're still going to be able to tell our power from the slope. And from the a value, of course, we're going to get some other information, as we'll see. So what we do is we take the period versus length data and we get the log of length in the log of the period. So we have log of period versus log of length. So we have a log y versus log x set of data, as we might have in the graph down here. Now we could graph this data, and we could then draw a straight line and estimate the slope and the y-intercept. What we actually did was we used derive to find the function. And the function we found for the log of the period versus the log of the length was, okay, our graph looks like this. We have a straight line. We could estimate, but derive gave us the specific function. Log of the period is negative 0.706 plus a log of the length times 0.498. And that's close to what we would get if we drew an accurate graph and estimated the y-intercept, which derive tells us is negative 0.706, and the slope, which derive tells us is 0.498. In that case, we obtain, well, taking 10 to this side equals 10 to this side. We see that we're going to have the period equals 10 to the negative 0.706 times the length to the 0.498. Now, I didn't write out the details of this. We'll look at details of another solution in a minute. But just raising each side to the power 10 and using the laws of exponents. On this side we're going to have 10 to the negative 0.706 plus a log of this times this. But the plus means that we have 10 to this times 10 to all this. And then this is a multiplication, so that we have 10 to something times something. We're going to call that 10 to the 0.498, or 10 to the log of the length raised to the 498 power, and we get length to the 498. In any case, the model comes out, the period is 0.197 times the length to the 0.498 power. Physics tells us that this ought to be length to the 0.5 power. And physics also gives us a value for this number out here. So here's a slick way to get the period as a function of the length.